So we now continue with the further discussion. So what method which we adopted to derive this is not a classical method. We tried to express it as the summation. We wrote as separate terms and then tried to find it out. But to start is alright. But in general we must have a classical solution. So I rub this out. This is not to be used. This is not the way we should be. Means we should take help of some simpler things, but we can't rely on them. We should be able to derive without going to these approaches also. So now what is to be done is, just by looking at these two terms, these two expressions, we should be able to derive it completely. So the issue is that what is available with us? Yn expression, that is the infinite term, non-iterative expression of Yn is available to us. Infinite term, non-iterative expression for Yn is available to us, and based on the infinite term, non-iterative expression, we need to convert it into a finite term iterative expression, and for that purpose, for iteration, a previous sample is of use. So we have taken y of n minus 1, we wrote here. Now how we approach classically? This yn includes a term which is not in yn minus 1 is xn, because that time when yn minus 1 was computed, xn was not available. So what I will do, this expression I will split. Xn means for k equal to 0. So this expression I will split into yn is equal to, for k equal to 0 I will bring the separate term. So when k is equal to 0, this is 1 and this is xn. So am I right? Xn plus remaining I will keep from k equal to 1 to infinity, half raised to k x of n minus k, no problem. Is it right? So what I have done? This was equation 1, expression 1. This is expression 2. So what is this? This is just rearranged. I rearranged expression 1 in this way. So when I rearranged it, it looks like this. Now I want whether I can express this in terms of this. So how I can do that? One thing is that this is 0, so it is 1. So I need to replace that. So what I will use in this, so I focus on, this I can rub out, you can go back and watch any time. This also I will rub out now, and I will focus on, or this I will write separately on both expressions. I will write on the left hand top. So yn is equal to summation k equal to 0 to infinity, half raised to k x of n minus k, and yn minus 1 is equal to summation k equal to 0 to infinity, half raised to k x of n minus 1 minus k. So these two are there. Now I will focus on this particular part. And I will try to establish what I am trying, what is the purpose. We should not forget the purpose for which we are doing something. What we want, we have rearranged this. So y is xn plus something, whether this plus something and yn minus 1, can I establish some relationship amongst these two? Can I establish some relationship amongst these two? So how I can do that? So what I will do, there are 2-3 approaches. What approaches we can adopt is either I can, so if I watch these two expressions, I find that this expression starts with k equal to 0, this one starts with k equal to 1. This is the difference. So how I can equate that? Now here I can't separate the term, because if I separate terms again it will be going iterative infinitely. So what I will do, I will replace the index. I will replace the index here. So put in this expression putting k is equal to 1. So I will put j equal to k minus 1. Putting j equal to k minus 1, what this becomes? This expression becomes summation j equal to 0 to infinity. J is k minus 1. So k is j plus 1. So it is equal to half raised to j plus 1 x of x minus into bracket j plus 1. I will write this again. This is equal to j equal to 0 to infinity, half raised to j into half raised to 1. So this half raised to j into half raised to 1, so this half comes out. Half raised to j x of n minus j minus 1. And now you watch these two closely. What is y minus 1? K equal to 0 to infinity, half raised to k x of n minus 1 minus k. So this I can same out. So I can write easily as minus 1 minus k. Right? So now these two are alike. 0 to infinity, 0 to infinity, half raised to k, half raised to j, same index, x n minus 1 minus k, x n minus 1 minus k. So this part is equal to this part, so half y. So this is half, so plus this is half y n minus 1. So thus y n is equal to xn plus half y of n minus 1. So this is a simple non-iterative finite. So I have again got to another limit of finite, only two term expression. Infinite term expression, a non-iterative infinite term expression is reduced to a simply two-term iterative finite expression. So any non-iterative infinite term expression which is given by formula can be converted into a finite term iterative expression. Now can its reverse is possible? So for that I will give you another example. And deliberately I will give you different example to check whether can you convert it into the transfer function. So what is in case of a system, current output is summation of current and previous inputs. If it is previous few, it becomes a simple system, high school level job. If it is previous all, then it becomes infinite term expression that can be converted into an expression using iteration. So an infinite system transfer function, that is h0, it has got all the h0, h1 to h infinity, that can be converted into an expression which uses previous output in its form. Now I will give you another one. Yn is equal to xn plus, half I can use, but I will use a general expression now. Ax of a is a constant. A is a constant, so you can have it any value. Yn is xn plus a, yn minus 2. From this you compute. So yn has to be always h of k x of n minus k equal to 0 to infinity. So previously what was given? Previously when hk was half given to you as half raised to k, from this, if hk is half raised to k, then yn is equal to, you computed xn plus half yn minus 1. So from infinite term iterative expression you converted finite term. So for infinite term non-iterative expression you calculated finite term iterative expression. Now if this finite term iterative expression is given to you, from this you find this equation will be given by what hk. It's very interesting. Now it's a high school scholarship level or NTS prelim level problem. Not impossible, but not so easy. From this, how will you find this? Yn is xn plus a yn minus 2. In that case, by what formula? Means this is a convolution expression which is containing of infinite terms. This is an iterative expression. An infinite term convolution expression can be converted into a finite term iterative expression, which we studied just now. Now the question is, how will you convert a finite term iterative expression into infinite term convolution equation? Those who want to check on their own should put a pause, have some groundwork and then verify their answer. You can pause and continue after you finish. Otherwise, we will continue. So here, how do we tackle? Obviously, there is a simple way. So this is, so here I have yn minus 2. So I will write yn is equal to xn plus a into yn minus 2 is what? Yn minus 2 is x n minus 2 plus a y of n minus 4. Then now we do by common sense, and then just like previous case, and then we do it by classical theoretical method. Then yn is equal to xn plus axn minus 2, this I will express, plus a square into bracket yn minus 4. What is yn minus 4? Yn minus 4, yn minus 4 is x n minus 4 plus a y of n minus 4 minus 2, n minus 6. So this is xn plus a x n minus 2 plus a square x n minus 4 plus a cube y minus 6 is x n minus 6 plus a y of n minus 8. So I can see a simple pattern by common sense. Common sense prevails, and it should prevail always. Xn plus a xn minus 2 plus a square xn minus 4 plus a cube xn minus 6 plus a raised to 4 xn minus 8 plus, obviously it will go like this, a raised to 5 x of n minus 10 and so on. So in general it should become, formula would be like this. Yn is summation of k equal to 0 to infinity. This is 1 for n equal to 0, for n equal to means current sample is 1. So when I have x of n minus k here, when k is 0, this is 1. So this is something like this. A raised to k, but not so clear. A raised to k, x of n minus k. So when k is 0, x n only. But when k is 1, it is not there. So this I can say k 0 to infinity, k odd. It is not a standard method. Odd. K odd. Sorry, not k even. K 0 to infinity. K even raised to, and now this is not a standard method. This we can convert later. I think everybody of you has agreed. So this is the expression. Whether this expression fully gives me this result? Yes. K1, K0, xn. K1, no term. K2, when k is 2, a raised to half, 2 by 2. So a, x of n minus 2. K3, no term. K4, when k is 4, a square, n minus 4. So this is the expression. Y is equal to this. Right? So now, but this we don't want. What we want? We want a clear-cut classical term. K should be 0 to infinity and you should have some expression. So what that expression can be? I think we end on this note that this can be a good homework for you. So before you come for the next lecture, you come up with this solution. So I think we appreciably covered many contents in today's session. We stop here. Thank you.